Good morning, everyone. Today's talk is about the first variation of the horizontal perimeter, and it decomposes into two parts. The first one is the preliminaries, and the second part is about our main topic, the first variation of the horizontal perimeter. And now for the preliminaries, we start with a three-dimensional contact manifold, M omega, where we have the kernel of omega as the horizontal distribution, and T is the Rib vector field, which satisfies the two properties here. Omega to T is 1, and the interior product d omega with T is 0. We keep the horizontal distribution with a positive definite metric, a family of inner products, and then we have a contact Sub-Riemannian manifold, M, the GH, and omega on M. And if we have an X and Y, an orthonormal frame on H, then the norms are of X and Y are equal to 1, and the two vectors are orthogonal. And we can extend the GH to a Riemannian metric G on M by requiring this tuph to be a unit vector orthogonal to H. So this means that the norm of T is 1, and T is orthogonal to the horizontal directions. Then, so we have the composition of the tangent bundle to the horizontal parts and the transverse directions. We can keep the horizontal distribution with an almost complex structure, practically a rotation by 90 degrees in the horizontal plane. Here, this is how the rotation acts on the basis, and we denote as C1, this quantity here is practically minus the inner product of the Lie bracket X and Y with T, and we can extend the almost complex structure J to the whole tangent bundle just by letting G to T to be 0 in the transverse directions here. Then we define this map, T Greek, from the tangent bundle to the horizontal directions via this formula here. So this quantity is the Ribli derivative of J, and we observe that it vanishes on the transverse directions, while it may not vanish in the horizontal directions, because the Lie bracket of T and W is of T and W is horizontal, because calculating omega to the Lie bracket of T and W via this the known formula here, we have that omega to W to be 0. Then this guy here is vanishes because omega T is 1, and by the properties of the Rib vector field, this quantity vanishes too. Then we have a generalization of the Tanaka-Webster connection here, which is a unique connection compatible with a metric with non-vanishing torsion, and the torsion is defined by this formula, and we call T, this map here, as the Sub-Riemannian or pseudo-Hermitian torsion. In order to not confuse the Levi-Civita connection with the nabla here, so we just denote the Levi-Civita connection with D, and we remind that it is compatible with the metric, and it is torsion-free here. And we also define this map here, sigma, from the tangent bundle to the horizontal directions to be this dVt here, and we remind that because this guy here lives in the horizontal directions, because from the compatibility with the metric, dVt, the product of dVt with T is 0 for every V, and we can have an alternative definition of J and T via the following equation. Finally, here are some properties for the torsion and the nabla, and we can compute the difference between the Levi-Civita connection and the pseudo-Hermitian connection here via these Koszul's formulas presented in this equation here. Let's go in the main part of today's talk about the first variation of the horizontal perimeter. First, we start with the definition of the singular set. If sigma is a C1 regular surface in M, we denote as n the unit normal vector to sigma, and the singular set sigma 0 of S is the set sigma 0 practically where the tangent plane is equal to the horizontal plane. We have this main theorem that the singular set has zero Lebesgue measure. And we remind from our previous talk that we denote as PH the canonical projection from the tangent bundle to the horizontal subbundle. And the horizontal projection of the normal unit vector is practically n minus the transverse part of n. And from now on, we denote the horizontal projection of n as just nh. So it follows that nh has this decomposition with respect to the horizontal frame here. These are the components of nh. And its normalization of nh is the horizontal normal unit vector here. We observe that for singular points, in sigma 0, then the vector nh calculated at p is practically 0, it vanishes. So so here this guy is not defined in the singular points. And so we work just for points that are non-singular. Then in a non-singular point, the intersection of the tangent plane with the horizontal subspace is practically a line. And we will construct an orthonormal basis of the tangent plane in these points. We just rotate the horizontal normal unit vector at the non-singular point P just by 90 degrees using the almost complex structure J. So we have this vector field here called the characteristic vector field in these points. And its integral curves are called just the characteristic curves. Z here satisfies the following properties. One can see that Z at P is an orthonormal horizontal vector, and also Z at P is a tangent vector. So we have a basis for this line here for the intersection of the two planes. By the definition of zeta, using the properties of J of the rotation operator here, we can see that practically the norm of zeta is equal to the norm of the horizontal normal unit vector, which is 1. Now, for the second property, in order to prove that zeta is also a tangent vector, we use the decomposition of n here via this formula. So n is nh plus the transverse direction here. Using the properties of the scalar product, we can see that this term here vanishes because we have a rotation of this direction by 90 degrees. And also this term here vanishes because T is a Riemann vector field and this guy here is horizontal. And then we define a second vector field, which is the second vector for the basis we want for the tangent plane. So S is defined by this formula. Here, this is the horizontal part of S, and this is the transverse part of S. And one can prove that at the point P, ZP and SP is an orthonormal basis of the tangent plane for a non-singular point, P. And we observe that the inner product of Z with S, using the definition of S here, taking the inner product with Z, vanishes. So the vector fields Z and S are orthogonal here because by the rotation this term here vanishes, and also this vanishes too because T is the Riemann vector field and Z is horizontal. And now it remains to compute the norm of the vector field S here, because we can calculate the norm of via its definition here, and using some elementary properties of the inner product, we can see that this term here is equal to 1 because it's the horizontal normal unit vector. This term here vanishes because T is a real vector field and NH is horizontal. And here this is 1 because T is a unit vector here. So we have practically the Pythagorean theorem using this decomposition again here. So the norm of S is equal to the norm of the normal unit vector in the surface and is 1. In this picture, we have what happens in a non-singular point, P. We have the tangent plane, TP sigma in the non-singular point P. Also, this is the normal unit vector and NP applied at the point P here. We project the normal unit vector to the horizontal subspace here. So we take the vector NHP and we make it, we have the horizontal normal unit vector, which we rotate it and we take the Z of P. And this line is just the intersection between the two planes here, the span of ZP. Here we have an example, an interesting example for the level sets. We start with a smooth function and we define the level set of U as the surface sigma. We call the characteristic set of sigma all the points of sigma that the horizontal gradient vanishes. And we remind by elementary differential geometry that the T sigma is practically the kernel of the U. And also from our previous talk, we remind that the horizontal gradient takes this formula with respect to the horizontal plane. Then the horizontal gradient vanishes practically when XU and YU vanish too. So this means that X and Y live in the kernel of the U, and practically we have that the horizontal subspace is a subspace of the tangent plane, and because of dimensional reasons, we have that the HP is equal to TP sigma, and in this case, for the level sets, the characteristic set is practically the singular set of sigma by the definition of the singular set here, that TP sigma is equal to practically to the horizontal plane here. And now we present some interesting properties, and we start with some identities that hold for every non-singular point. The first identity here follows from the Pythagorean theorem, practically, this from the decomposition of the normal unit vector to the horizontal part and the transverse part. Here we have this that is equal to 1. So we apply the vector field Z on both sides, and we take the second identity after using the first and the Pythagorean theorem again. Now, in order to go for our main theorem, we just need some things from elementary differential geometry. And we remind that for every basis L, let's call it E1 and E2 of the tangent plane, the area of the parallelogram created by the two vectors is just the quantity here. This quantity here is the square of the gram determinant, the square root of the gram determinant. And we need this lemma in order to prove our main theorem here. Let sigma a C1 smooth surface on M and a point P on sigma. Also, we have a basis E1 and E2 of step S, and we define this tangent vector at the point P. This reminds us the Grassmann identity here. So we have practically this equation, which gives the divergence between the two planes, the horizontal plane and the tangent plane. We take the advantage of the decomposition of the tangent bundle Tm to the tangent parts of sigma and the normal parts here. Then we can write the projection of the normal unit vector to the horizontal space as we can write it as a combination of a tangent component and a normal component. So we just need to find these two coefficients here, lambda and m, and take the norm in order to prove this identity here. First, we use the fact that H and T, because T is a Riemann vector field, and this guy here is horizontal, is 0, by applying the inner product in the equation 1 with T. And then we have, it follows using the definition of H here that we have the second equation. Also, applying the inner product in the definition of H with each one of the vectors of the basis, then we can see that here by using H, we can see that the inner product of N with E1 and of N with E2, because E1 and E2 are tangent vectors, they vanish. So we take the third equation here, and we solve the induced square system for lambda and m after taking the inner product in the first equation with E1 and E2. Lambda and m can be calculated here via this formula, and then we can substitute back into the second equation, taking the norm and prove this identity here, which we'll need it for our main theorem. And now we can go to the definition of the horizontal perimeter of sigma, calling it AH of sigma. Is practically the integral of the norm of the projection of the normal unit vector to the horizontal directions. And we remind that if S is the boundary of a set T, which is a measurable set, and omega is an open set of M, like in the case of the Heisenberg group, this definition here of the horizontal area practically is equivalent with the definition of the horizontal perimeter of E in omega described in the book of Caponia here. This definition of the horizontal perimeter we described in our previous talk. And so the horizontal area of sigma is equal to this. This is a remark of Rittore and Rosales in a paper of them. So we can define the horizontal area functional now. We have all the ingredients ready. We start with sigma, a surface, an oriented regular surface. And we have M, our contact manifold, which is three-dimensional. And we have also a vector field U with a compact support on sigma, and which corresponds to the one-parameter family of diffeomorphism, phi sigma, phi S of U, calling it just phi S. Then the horizontal area functional associated to U is defined just by the horizontal area of the S tilde. It's just the moving of the surface S using the one parameter family of diffeomorphism. So we just denote it as tilde S. And the first variation of the area functional associated to the vector field U is defined just by the derivative of the horizontal area with respect to S, calculated for S equal to 0. So we have our main theorem here that the first variation of the area function of the horizontal area functional associated to U can be described by this crazy formula here. We can find it on a paper of Matteo Galli and I think Rittore. The proof has some. We can describe just a sketch of the proof in 2 steps. So we have in the first step that for every non-singular point, we start with an orthonormal basis of the tangent plane, the basis ZP and SP we described previously. So we can extend this basis to vector fields Z and S along the curve here, using the flow of the vector field U. The starting point is the point P here, and the starting basis of our tangent plane is practically E1 at 0 and E2 at 0, just the vector fields ZP and SP. So we can move them using the push forward of ZP and sp, and we can create the two vector fields E1 and E2, which remain invariant under the flow generated by U, because taking the Lie bracket of U and EI here, we can use the definition of the Lie derivative and then use the definition of E1 and E2. Here, there is no, this equation is independent of S, so we have that this term here vanishes. In the second step, we observe that the surface area measure here for the surface sigma can be described in a local coordinate system by this formula, because we start with an orthonormal basis here. This is practically 1, the area of the square here in the point P of the unit square, and then we just compute the pullback of d tilde sigma using the one parameter family of diffeomorphisms here. So we have that the surface area measure here can be described by this formula here by some computations. And in the third step, we just want to use the lemma here, this lemma here. So somehow we need to construct a vector field of this type, of this Grassmann type, let's call it. So we define the vector field Vs here, and then we can use the change of variables formula. And so one can find that because Vs is of this type, then the norm of H is practically the norm of Vs, this quantity here by the lemma. And so we can also substitute the surface area measure d tilde s, and we take this quantity. Then these two guys here can be deleted. So we have that the horizontal, so we have that here, the horizontal area functional is practically the integral of the integral sigma of the norm of Vs. So we need to calculate the first variation of the horizontal area functional. We just want the derivative with respect to S and then calculate it at 0. And we use some properties of the covariant derivative here. And using the previous definitions, we just need to compute the norm here on the denominator, and also this inner product. We have that V for S equal to 0 practically is here this scalar of Z. And so the norm of V at 0 is practically the norm of H. Using the properties of the Levi-Civita connection, we can calculate the duv at 0, and then we can calculate the inner product here inside the integral. Now we can combine these two with the integral, so we can calculate the first variation, which takes the following formula. Then after some computations, we can use the left invariance of Z and S, the starting definition of the generalized pseudo-Hermitian torsion we described in the start of our talk, and we can decompose the vector field U to a horizontal component and to a transverse component, which completes the proof in the last step. So we prove that the first variation of the area functional associated to U receives this formula here in equation 5. But in the special case where U is practically a normal vector here, we have the following corollary, that the first variation of the horizontal area functional takes this formula here, where here the divergence is the divergence of sigma, and when U has compact support inside the S minus S0, we have that the first variation of the horizontal area is practically just this integral, because we can use Gauss divergence theorem for sigma, then this term here vanishes, and just this term, it's the definition just of the horizontal mean curvature, which is equal to the horizontal divergence of the horizontal normal unit vector, which is equal to this quantity. So if we have a surface sigma, which is area stationary, this means that the first variation is 0. So we have that the horizontal mean curvature vanishes in the non-singular points. Also, the converse is true. And we finish with an example in the Heisenberg group. We start with the local frame of the horizontal distribution, x and y. We can consider planes of this form here. It is easy to calculate the horizontal normal unit vector, and then we can calculate the horizontal mean curvature, which is 0 for these planes. So we have that this is an area stationary for the first variation. Thank you for your attention.